Thank you very much, Giovanni, and thank you for the patience. We eventually made it. So it's a pleasure to be here. So this is the title, and I will start from the end, just to tell you where we're going to land. And this is what I'm going to create mathematically. Right. So this is a beating heart. I think it's the first time in the world that we have a complete beating heart which produces quantitatively correct results, which is very, very difficult. And you see, well, we'll have the time to discuss all the details later on, but this is what we are going to have at the very end of the story. Right. So it's a mathematical story, and of course, to simulate the heart, you need to know at least what is absolutely essential for understanding the heart beating. So this is a picture of the heart. The heart is typically qualified as being a pump, which is a kind of very reductive description, but it, of course, it has some truth inside. The heart is made of 4 chambers, atria, right atria, left atria, and ventricles, right ventricles and left ventricle. There is the venous blood that comes from the body through this vena cava, the inferior and the superior vena cava. It enters into this part, which is the right heart, the right atrium. Then there is this valve that opens and allows this blood to enter into the lower part, which is the right ventricle. And then when there is the systolic phase, which means the contraction of the heart, remember that every second of our life we have contraction and the relaxation of the heart. When there is contraction of the heart, the blood that is in the right ventricle will be ejected into this vessel, which is the pulmonary artery, and it goes to the lungs, where it releases the CO2 and the other toxic substances, and it intakes oxygen, and brings it back to the heart. Through 4 vessels, these 2 and these 2, which are called pulmonary veins, it enters into the left atrium, and when this, say, 3rd valve opens, this is the mitral valve, this blood will be squeezed into the left ventricle, and of course this will relax to allow as much volume of blood as possible, and then when it squeezes, you will have that this blood will be pushed into this ascending aorta, and through the ascending aorta it will reach all the billion of cells in our body. So essentially, this is what happens. The point is, why do we have these 2 mechanisms of contraction and relaxation? I mean, of course, it's a pump, but when you have a pump, you have to provide energy to the pump, right? If it is a bicycle, you have to provide your own energy. If it is an electrical pump, you have to plug it somewhere. And the origin of this energy comes from an electrical stimuli that occurs here. So at every second of our life, there is a spontaneous electrical stimuli that generates an electrical field, which propagates first through the atria and then through the ventricles. And for some magic reasons, thanks to God or Mother Nature, depending upon your point of view, at every cell of the cardiac muscle, you have the opening of the channels, ion channels, and you have ions of calcium, of potassium that goes back and forth through the membrane of the cell. This creates a say, cross-membrane potential. We generate a force, which is called active force, at every single cardiomyocyte. This single cardiomyocyte, which are microscopic structures, relaxes or contract. They generate a train of waves that propagate, and eventually you will have the complete contraction and relaxation of the system. So that's why we have our heart beating. And of course, mathematically, we like to represent all this in mathematical terms. So this is what we are actually doing. We start from, we want to address clinical problems. And I will not talk about clinical problems this morning. I will talk about them this afternoon in the lecture that we'll give to later on, say. But we start from clinical problems. and we want to deliver a mathematical solution to that. So we'll go through the pre-processing, which means creating the data that will then be useful for the mathematical model, create the mathematical model, solving it numerically, and hopefully, say, with the help of artificial intelligence algorithms, say machine learning algorithms, simulate what happens and deliver the solution to the clinicians. This is the whole path, say. So I'll go through all these points, and I try to be fast because every single point would require, say, a lot of investigation. But just to give you an idea, where are the data coming from? Well, they come from clinical images, and we have to go through segmentation, registration, generating surface meshes, volumetric meshes, generating the fibers, and being prepared to then to feed with this data the mathematical models. We start from images coming from patients, so CT scan, CMRI, late gadolinium enhanced MRI or phase contrast MRI, and we use them to generate shapes, motion, and scars in case where the heart of a single, this is a left ventricle, where you have been, say, the patient have been experiencing I don't know, heart attack or some problems like this, which generates, say, induces the fact that some of the fibers will be necrotic, so they will not be able to conduct the signal anymore. And we want to reconstruct this pattern where, say, the red zones are the healthy zones, the scars, the black, are the parts of the body of the, say, myocardium of this ventricle that are not conducting anymore, and then you have a gray area. So we use data to generate this information, and we use data to generate boundary conditions, and this is a very critical issue when you solve a, say, mathematical problem, partial differential equation. You need boundary conditions, and typically we take it for granted, but how do you generate boundary conditions for the heart? Of course, you cannot pretend, say, the patient to undergo invasive and intensive radiological exam to generate boundary conditions. That would be ridiculous, right? You'll never be able to do that. And you have many boundaries. So this is just an example of the many boundaries that you have, depending upon the type of model that you are going to use. You have external boundary, you have internal boundaries, you have boundaries coming from the fact that you are cutting the veins on the arteries and you want just to simulate the heart, but the heart is in the middle of the whole system, so you generate artificial boundaries. And every time you are led to the problem of generating boundary conditions that are realistic. That's a very big problem. I'm not insist on that, but this is one of the, say, difficulties of the problem. And then you have other difficulties. For instance, the fibers. The fibers are extremely important because they allow the electrical signal to be propagated from one side, so they're very fast highways for electrical propagation. And on the other side, they have to create torsion to allow our heart to eject as much volume of fluid as possible. So knowing the fiber distribution is extremely important. And these are not known. Again, these are extremely important data that you do not typically have because these are not provided by the classical, say, clinical imaging procedure. Of course, there are hospitals with the diffusion tensor MRI. You can have a hint of that, but this is not in the availability of all the hospitals. So typically you do not have this type of information. And it might look paradoxical, but this is one example where we solve partial differential equations to generate data that are missing, instead of using data to generate the solution of partial differential equations. So there's a pre-processing where we solve level set method, using level set method to generate boundary data. To generate the fiber distribution that are then useful in the modeling. And what is important is that each one of us have different type of distribution. You have the distribution of the fibers on the epicardium, which is the external surface of the heart, and a different type of distribution of orientation in the endocardium, which is the internal part of the heart. And you have transmural variability. And with this method, we generate this transmural variability, which is so important to generate realistic results for specific patients. So this is the pre-processing, and is an issue in itself. And then you have the modeling. Modeling means trying to reproduce the complexity of the heart in terms of function. So we want to reproduce the heart function and also the heart dysfunction in case you have pathologies. So this is, say, the list of the different physical processes that occur in the heart. And you have to model all of them. So the first one is the electrophysiology. You want to generate the electrical field. And we start from cells. This is a multi-scale problem. We go from the cell level to the organ level. So it's a multi-scale problem in space and time. So at the cell level, we want to describe the dynamics of the ions that go back and forth from the ion channels. And this is a system of ordinary differential equations. We have to model this ionic flow, and we have to do it under the action of the so-called action potential. This is millivolt, and we are in the left ventricle. We start from, we have contraction and relaxation. We start at time 0 at the end of the relaxation phase, where you have the maximum expansion of the heart. We are here. Everything is at rest. And then you have the heartbeat, which is a spike. So you have a depolarization, followed by a plateau, and then a repolarization. So we want to simulate what happens to the ions under these actions. And so we need to solve differential equations. And you have many different types of models. Some of them are purely phenomenological. Others are based on experiments and try to interpolate results from experiments. There is a library of models that are available here. And what is important to remark is that cells in different places of the heart behave in a different way. So if you're studying the ventricles, you have to use specific models. If you're studying the atria, you have other models. If you're studying the septum, which is the separation between left and right heart, you have to use other models as well. Then you want to propagate the electrical signal, and then you solve the problem, which has this form. This is a partial differential equation. Actually, it's a system of partial differential equations. In, say, the classical classification, typical classification, is a system of nonlinear reaction diffusion equations. The solution of this problem is the transmembrane potential and the extracellular potential. And if you solve this problem, which is in dialogue with the previous model through this ion variable, so it's coupled to the previous system of ordinary differential equations, then you will be able to reproduce the diffusion of propagation of the electrical field in the ventricles. So this is the electrophysiology part. So if you are in dialogue with the doctors that are, say, responsible for the pathologies due to the heart rhythm, this is what matters. Okay, what comes afterward is not their field. Right? It's a field of other doctors, other cardiologists. So this is the generation of the active force at every single cardiomyocyte. Is again a system of ordinary differential equations where the unknowns are the state of the contraction and the sarcomere length. And again, here, this law is not, the one that we are using is not written in the rock. There is still a big debate in that. And the model that we are using is actually, we'll see later, inspired by and say, obtain with the help of neural network to generate constitutive laws where we do not know them from the physical point of view. So this is the system that generates the active force. And this is the system that generates the deformation. This is the passive mechanics. When you have an object, a mechanical object, an elastic object, you apply a force and you know that it deforms, right? You have a bridge, for instance, or just say iron, whatever, you apply a force with a certain intensity, will have deformation. So the heart does not escape to this rule, is a solid material, so you apply the force which is induced by the fluid, which is compressing and relaxing inside, so you have the deformation of the heart. And this is the classic elastodynamic equation, although the Cauchy stress, those who know about, say, continuum mechanics, we have the Cauchy stress, which has very specific form here, is the sum of the classical Cauchy stress for the passive component plus the active component, which is the one that I've been described before. So we're assuming that The material is orthotropic and hyperelastic, which means it's a very specific material. It's not like having an iron or a bridge or concrete, say. Again, constitutive laws that are under exam here. But we assume this specific behavior. We assume that the blood is nearly incompressible. It's not, sorry, not the blood, the solid part, so the myocardium is nearly incompressible. It will be perfectly well, it's made basically of fluid. So it would be fully incompressible if you would say, if it would undergo the law that the divergence of the velocity is equal to 0. This is not the case. It's nearly incompressible. So you need to adopt, let's say, specific numerical methods for treating the nearly incompressibility. The issue of boundary conditions is terrible, in the sense that you have to generate boundary conditions on boundaries that are not physical boundaries, that are artificial boundaries, and this is extremely easy to generate wrong boundary conditions and to tune them in a bad way in order to have a solution that has nothing to see with the real solution, say. So we have proposed different type of boundary conditions which are non-standard in order to close the system. And then we have, so far, the electromechanics model that you see here. So those are the different components I've been talking about: the ionic activity, the electrical activity, the active and passive mechanics, and the force generation that are in connection one another. So now we would be able to let the heart contract and relax, but of course the heart is not in the middle of nowhere. There is the external circulation, and we mimic the external circulation through a system of networks, electrical networks. Mathematically speaking, this is a system of ordinary differential equations. So when you couple all together, you have what is called the electromechanical model. And with electromechanical model, you can reproduce the heart beating. Okay? It's a multiscale problem. Go to the cell membrane, to the cardiomyocyte, to the cardiac tissue. So it's a multiscale in space and in time. You have different scale of, say, space dynamics and also temporal dynamics. So this is a heart beating. However, we are cheating here because we have not yet solved the fluid dynamics part. We are just representing the fluid dynamics through the pressure that blood exerts on the internal, say, membrane. But we want to compute it by solving three-dimensional methods, three-dimensional models, and that's why we have to use the fluid dynamics. Right? So we have to use the fluid dynamics to solve the flow equation in a domain that is moving, because the heart is beating. So it's not like solving the problem in a channel or in a bottle, say. You are solving the problem in a domain that is moving, and this is deforming under the action of the electromechanics that you have seen before. So we're solving the Navier-Stokes equations for incompressible viscous fluids in a moving domain. And of course you need to account for the dynamics of blood. So this is an atrium. This is the left atrium. What you're representing here is the vorticity. You use the velocity field, and this is the curl of the velocity field. This is expressed in 1/2, and we go from 0 to 800. Say you can appreciate the generation of vortices. The point is that you have the valves. And you have to account also for the valve. You see, this is the left part of the heart. You have valve here connecting the atrium to the ventricle. This is the mitral valve. And then you have the aortic valve, this one, which is the one connecting the ventricle with the ascending aorta. So the valve here are represented as resistive terms on the momentum equation of Navier-Stokes equations. So the fluid dynamics see the valve as being resistive objects in the domain of the fluid. And these resistive objects are basically some, say, delta Dirac function that operate on the valve leaflets. And here you have the difference between the velocity field of the blood and the velocity of the rate of deformation of the valve, say. So this is, we call it the resistive immersed implicit surface method for valves. And this is a way we simulate the fluid dynamics, accounting for the dynamics of the valves. By so doing, we are able to reproduce all the critical phases of the heartbeat. You see here the arrows describe the direction of the blood from the right part to the left part. So what you see on the left is what doctors call the right heart, because it's on the right of our chest, right? So we have the isovolumetric relaxation, the ventricular filling, the atrial contraction, the isovolumetric contraction, and the ventricular ejection. And doctors are very familiar with these curves. And these are called the pressure volume loops. When they see this curve, they immediately understand whether or not this patient is performing correctly. And here you are reproducing the pressure of the ventricle, for instance, when you change the volume due to the deformation, the contraction, or the relaxation. So these are perfectly functioning heart for ventricle. The same curve for a LTR for atria is totally different. We have this 8 loop, say. And when you look at these curves, again, doctors are immediately capable of detecting the say, physiological or pathological behavior of the heart. And we have been able to reproduce them quantitatively in an exact way, say, well, very accurate way. This is the last model, part of the model is the perfusion. I guess you all know about coronaries. Coronaries are sitting on the external part of the heart, and they are there to feed the heart, to feed the muscle. So they take blood from the ascending aorta, and they bring blood back to the muscle, to nurture the muscle. Those are the coronaries that you can reconstruct from medical images. The scale is of the order 1 millimeter, but coronaries that have a diameter inferior to 1 millimeter that cannot be detected by medical images. And still we know that our heart is plenty of coronaries, right? So we have to reconstruct them. So we use artificial methods to reconstruct the coronary bed. We have about 80,000 coronaries that enter into the myocardium, and we use a multiscale analysis for the perfusion. Perfusion is the action by which the blood is perfusing the myocardium, is nurturing the myocardium. So we are solving Darcy equation as if it were a porous medium, but we solve it in 3 different scales. So at every single point, we are assuming that you have the presence of coronaries of different sizes. And we have to let all these systems interacting one another, say. So this is a complete picture. I want to give you just a view on what we are doing on a specific heart. We have the electromechanics, we have the fluid dynamics, and we have the perfusion. And this is all what describes the functionality of the heart. I told you before that the heart is not in the middle of nowhere, so we have to construct a system of ordinary differential equations that are inspired by the analogy with electrical systems, with electrical circuits, to reproduce the dynamics on the rest of the circulation system, or the circulatory system. And the two things are obviously connected together. Then we want to generate numerical ECG electrocardiograms. If you experience to go to a hospital because you have some troubles with the heart, you see that the very first thing is to doctors would like to see your electrocardiogram, your ECG. So they put lead on you and they reconstruct the potential. And then, of course, through an inverse program, which the doctor is not aware of, he has to reconstruct, to guess what is the potential in the heart, right? So you see the potential on the chest, but you have to reconstruct, say, the potential in the heart. So we want to construct numerical ECGs once you have solved the problem in the heart. So we have the heart coupled with the torso, you are propagating the signal in the torso, and you account for the different materials that you have in the torso. So you have bones, you have fluids, you have solid material, and you generate, say, the electrical ECGs. So this is, as far as we know, the first complete model of the heart ever. We account for all the dynamics and all the processes that occur in the heart. Now, how to solve this monster system? That's the point, right? So we need to go to the numerics, and of course here I'm not going to provide you any detail, but say at the end of the day we're generating a library, which is a research library that is, say, capable of addressing all these complexities and solving the problems. And so we have different type of methods for the different processes that are there. I will not insist on that. We have different problems coming from one side, from the issue of stability. We have a multi-scale problem in space and time, and on the other side we have a gigantic system of equation, non-linear stiff equation to solve that. You have to separate into different physical processes, and we have to account for all of that. So there is a lot of, there's many issues about stabilization here, and there is many issues about how you solve these algebraic solvers. And you need, of course, parallel preconditioners if you want to go with parallel computing, which is unavoidable to address this type of complexity. So very complicated issue here, but I will not insist on that. And this is the library, and so far we have 15 active developers, 150 users and collaborators around the world, and this is an old picture, 120,000 lines of code. I guess that now we are about the double. We have about the double. So it's an increasing effort. Simulation. Just to give you some idea of what we have been able to do. This is something doctors are very familiar with, this picture here. This picture here. So what is this picture? This is the activation map. They are familiar with this because they have engineers in their rooms, in their operating rooms, and the engineers are capable of reconstructing the activation map by software which comes from the medtech industries. What is the activation map? Well, it's this map here where you have isolines which connect points that are electrically activated at the same time. So this is a healthy heart, and these are nice isolines. Here you see the propagation of the electrical field. And here you see the same isolines, but dynamically. You see the propagating front. You generate electrical stimuli here. It propagates first to the atria and then to the ventricles. So this is something they are used to, doctors, and this is something which is completely new for them, also this one. And of course, it's important to reconstruct them in pathological scenarios. This is the calcium concentration. The calcium is the main trigger of the contraction at the cardiomyocyte level. So this is the dynamics of the calcium. Of course, there are scales where you have in micromoles, you see the way the calcium is behaving in all the heart. This is a cross-section of the heart, a longitudinal cross-section of the heart, and this is the heart seen from the outside, say. This is the active tension. The active tension is the force that is generated on every single cardiomyocyte during a heartbeat. And this is the complete dynamics of the heart. You go in this case from 0 to 16 millimeters, which means 1.6 centimeters. So it's a big deformation. In engineering terms, it's a big deformation. This is the fluid dynamics. This is the left ventricle and the left atrium. You see the way blood is coming from, say, the 4 pulmonary veins in the upper part. Now and then, when this opens, it goes in the lower part, which becomes larger and larger until when the pressure will, say, win the resistance of this valve, which is the aortic valve, and blood will be pushed into the main aorta. What you see here is the structure of the vortices. This is meter per second, so we go from 0 to 1, which means, roughly speaking, 36 kilometers per hour. This is a healthy heart, right? And the issue is whether this blood is turbulent. In normal conditions, it is not, but it's in permanent transition toward the turbulence. You do not have the time to fully develop the turbulence because there's not time enough due to the heart beating, and neither space enough because you have, say, of course, a limited space. But it's in permanent transition, which means that also numerically you need to develop numerical methods that are appropriate for treating this type of transition. And this is the complete fluid dynamics in the complete heart, say. Perfusion, what we are trying to do is to replace the cyclet. So if you are old enough, luckily it's not your case, it might happen that you have problem of going to the hospital because you say, I have a little problem with my heart rhythm, and the very first experiment is they put you on a cyclet and you try your bike, and then they regulate the intensity of the force, and they see the way the pressure is changing, right? Now in the most advanced, cardiological divisions, you have a more intelligent cyclet. They do not only detect the pressure, but also they make an echo analysis while you are biking. And to do that, they have to inject a contrast liquid, which is of course toxic. And once doctors came and asked us to try to create a kind of mathematical cyclet, can we reproduce the exercise mathematically? And this has potentially two benefits. The first one is that you do not have to inject any liquid of contrast, which is toxic. And the second one is that you can tune your, say, model and increasing the effort that is required without jeopardizing your health, right? So with no risk. And so we have been able to, for 9 patients so far, to see that the perfusion that we are actually computing with the numerical cyclet is within the 2%, the same as error, the same as the perfusion that is measured on patients. So everything has been validated. I will not bother you with all these numbers, but this is what we have been doing, and in the end, so far you have seen. I mean, all what you have seen is what can be called a physics-based model, right? So all those models are based on understanding the physics and trying to reproduce it mathematically and solving it numerically. And now there's a newcomer, which is machine learning. Well, new for us because we're completely naive on that. And in the past, say, 2 or 3 years, we tried to embed, well, see the way machine learning algorithms could help us. And the way we intend it is in a cooperative manner. So it's a cooperative game between physics-based and data-driven algorithms. We want to let these 2 water drops to, say, go into the coalescent drop. And of course, there are many different possible, say, benefits that you can get going from one way to the other and back. One is regularization by inserting, for instance, for the networks, say, machine learning or neural network, inserting in the loss function terms that depend on the residual of the differential model. Data augmentation in case you have scarcity of data, which is very often the case in the medical context, to augment the data by solving, say, the problem with the physics-based model. So on the other side, model reduction, you have to go from a gigantic system to very small systems. Well, what I didn't say is that to simulate a single heartbeat, which is 1 second of real life, it takes about a couple of days on a big supercomputers, right? So 1 second, a couple of days on the cluster of about 200, say, cores. So if you want to create a dialogue with doctors, you have to be more, you have to be faster. And to be faster, it means that you have to, say, either wait until you will have a computer that will be more and more powerful, but this is not the right attitude. Otherwise, try to speed up your computation. And the way you speed up your computation is through generating, using model order reduction and generating problems of much smaller size. However, retaining the basic features of the high fidelity model. And in this context, machine learning could help. Uncovering constitutive laws, where you are dealing with material like myocardium, where you do not know the constitutive laws, try to help experimental analysis to compute not the constitutive law in analytical terms, but the input-output section. So for a given displacement, what kind of for a given deformation, what kind of stress, or vice versa, say, or for parameter estimation, sensitivity analysis, etc., etc., etc. So try to have these 2 words in dialogue, and of course here it's is not for beginners because everyone thinks today to be able to use machine learning algorithms and neural networks, but this is actually not true, especially when now I report in my own experience. When you start from say, your own culture, which is only based on physics and mathematics and PDEs and numerics, and you try to use machine learning, you can immediately make terrible mistakes, right? So you really have to dominate the problem, and I'm not saying that we are doing that, just saying that we are focused on the solution of this specific problem. We try to, say, to be helped by machine learning approach for that. So we We use it for model reduction, for model learning, for parameter estimation and calibration, for sensitivity analysis. That's the way we use it. Right. And here are just some examples that I will not discuss them in detail, but it's just to let you know some of the cases where we have been using machine learning algorithms in connection with physics-based algorithms to solve specific problems. Here we want to understand the dynamics of the generation of the force, at the level of every single cardiomyocyte. And by this, we can really, have a very substantial gain in terms of computational time. You go from 20 hours to 2 hours in this case, and we have a very substantial saving in memory usage. We develop multi-fidelity physics-informed neural network to estimate the ionic parameters. When you try to solve this mathematical model for the heart, you have hundreds of parameters that are patient-dependent. How do you estimate them? Of course, you cannot pretend having measures to estimate those parameters. So we use multi-fidelity physics-informed neural network to minimize the less function that are weighting the discrepancy for low-fidelity model, and second, say you use an artificial neural network, and the second one, which is trained on pre-computed numerical data, and of course you have noisy data. You have to account for the noisy data and for the error in the few data that you have available. We use reduced order models to simulate the pressure volume loops in the one that connects, say, the diagram that connects the pressure and the volume in every single heart chamber. We are able to reduce by a substantial amount of time the computation in order to provide not the complete solution, but that specific diagram, which is helpful for doctors. I don't know what happens. Okay. We use artificial neural network as a surrogate to describe the left ventricle electromechanical function. We have artificial neural network for global sensitivity analysis. This is just an idea. This matrix contains in the on the rows 36 parameters. So those are the parameters that we're using for this specific simulation. And on the columns, you see 20 quantities that you like to measure to provide doctors with, right? And you want to see which are the parameters that are most influential for every single quantity that you want to provide. So we are using, as you see, artificial neural network, Monte Carlo method. Well, we have a sampling of the parameters and use Monte Carlo method to solve this. And if you go with brute mathematical force, it will take forever to take using 160 cores simulating 740,000 heartbeats. It will take for say as much as 68 years. And here it takes 7.5 days to have the same computation. We use a Bayesian approach for parameter estimation. We use reduced order models to compute simultaneously to approximate simultaneously the manifold of the solution when you change the set of parameters. This is based on Galerkin projection, followed by, say, deep neural networks for the approximation of nonlinear operators that enter into the projection here. We use physics-aware neural network for inverse problem, where you want to go from the measure that you have on the chest and reconstruct the electric potential that you have in the full heart, and so on and so forth. I hope I gave you an idea of what is behind. Of course, I did not pretend to give you any detail and insist on any detail, but I hope you have the idea of the complexity and of all the uncertainty and the mathematical difficulties that are behind this type of investigation. So thank you very much.